we introduce a novel problem, identifying outlier arms in multi-arm bandits. A multi-arm bandit has n arms. Each arm has a distribution to generate rewards, which is unknown, and it has to be estimated by pooling the arms and obtaining samples from the distribution. Based on the samples, the system can calculate the estimated expectation of each arm and its confidence interval. In this study, we focus on a novel problem, which is to identify arms with abnormally high reward expectation called outlier arms. The outlier arms are defined based on the classic K-sigma rule, namely arms that are K-standard deviations away from the mean of all the arms. The objective is to design a sampling strategy that can output the correct results with high probability by pooling the arms as few as possible. This problem has many applications, such as identifying side effects in medical experiments or screening for network failures. This problem is non-trivial because not only the expectation of each arm is unknown, but also the outlier threshold function, since it depends on all the arms. This poses a double exploration trade-off. The sampling strategy needs to balance between efficiently identifying outliers and accurately estimating the threshold. The former requires to sample more on specific arms that are close to the threshold, while the latter favors to sample all the arms uniformly. A simple baseline is the round-robin algorithm, which pulls each arm from 1 to n iteratively, and stops when the confidence interval of the threshold no longer overlaps with any arm's confidence intervals. We upper bound the total number of pulls, which is related to the hardness term h1. h1 is inversely proportional to the square of the minimum distance between any arms and the threshold. We propose a weighted round-robin algorithm. It visits arms in a round-robin fashion but pulls more if an arm's confidence interval overlaps with the threshold's confidence interval. For this algorithm, the upper bound is a combination of hardness terms h1 and h2, where h2 sums over the reciprocal of the square of the distance from each arm to the threshold, which could be much smaller than h1. Our experimental results on both synthetic and real-world dataset shows that the weighted round-robin algorithm can substantially save cost from baselines like round-robin. Our poster will be presented at NIPS 2017 on Wednesday's poster session at 6:30. Welcome!